Thanks for the kind introductions. So this is CoSMIX, a joint work with Jan, Christof, and Mark. Let's begin. So we all know the night is dark and full of terrors. But is it the night or the cloud, where adversaries can lurk inside our machines? Luckily, recent development in hardware enclaves can help us. The way to do that is that they shield applications from privileged adversaries, providing them confidentiality and integrity, so they can't, even a malicious OS cannot read them or tamper with it. And recent development in library operating system even allowed us to run unmodified application inside of enclaves, such that every request made to the operating system will be passed through the library operating system, and we'll be able to validate it and pass it on to the enclave seamlessly. This current talk will focus on the current architecture of SGX enclaves that are integrated into recent Intel CPUs. And the question we asked ourselves was, can we execute any application inside of enclaves? Unfortunately, the answer to that is no. And as an example, we look at memory mapped files. So SQLite has a way to fastly read the database file by memory mapping it to its address space. Then it will just access the memory as it did with any pointer to read the file, the contents. This will trigger, if the page is not physically available, a fault handler that will read the page contents. And this does not apply only to file mapping. Previous works have shown that you could achieve disaggregated memory support, compressed memory, and many other things, because customization is a powerful tool. And because it's so efficient and require no modifications for applications, the way that applications are programmed right now is that they rely on these abstractions. Unfortunately, it's not possible to do it in currently available SGX. The reason is that the fault handler is untrusted as it's part of the operating system. So we can't use it and customize it as we would with traditional applications. We also can't use the available SGX demand paging instructions because they're inflexible. What we can do is try to use an in-enclave handler. Unfortunately, that doesn't work either. The reason is that, first, it's inefficient. So let's take the following example. On each fault, we'll need to first exit the enclave to the operating system. We'll enter into an exception handler in the enclave, resolve the fault, exit again to the operating system fault handler, and resume the execution of the enclave. Even for an empty fault handler, this is 2 enclave transitions, which are known to be very costly. Apparently, it's 6 times more costly compared to traditional page faults that we measured. The second problem is that every time you take a fault, when moved to the operating system, it might resolve the fault by itself, resuming and replaying the last instruction without the enclave being made aware that the fault handler never was executed. And the key point is that enclaves are really missing an OS abstraction that applications relied on. And previous work comes to show that they sidestepped this lack of secure page fault handler to create in-enclave paging support, oblivious page accesses, and secure access to remote memory, and many other things. These were all ad hoc solutions that required modification to the application to support them. And the question that arises is, well, what if we want to add more than one to the applications, right? We could use a customized and efficient page fault handler, and we have an opportunity in our hands if we would be able to do that. So to recap, application needs efficient page fault handling support, yet we can't rely on the current hardware. So what can we do? Well, we can automatically change our applications by instrumenting their memory accesses. And this is exactly CoSMIX that I'll show next. CoSMIX is an efficient instrumenting compiler and runtime system. And our basic observation in this work was that, well, we don't really need to instrument every memory access. So take, for example, the memory mapped files. We don't need to instrument stack memory, right? So we decided on an instrumentation policy that reduces the overload on the programmers. So they only need to annotate memory allocations that define the memory semantic to that memory regions. And CoSMIX will automatically infer the memory accesses that needs to be instrumented and how. But the question is, how should we express the memory behavior, or what is the interface that is needed to support custom page fault handlers, right? We need a new software abstraction. And this is memory stores, or in short, mem stores. Memory stores are another layer of virtual memory on top of an abstract backing store. And backing store can be anything. It could be the volatile memory, a persistent storage, even remote memory in the cloud. It doesn't matter. Virtual memory, on the other hand, is much more interesting. So the basic interface for memory stores, or to support virtual memory, apparently, is to support allocation and deallocations, which means we need to instrument and provide callbacks for memory allocations. And the second part is to provide address translation and a paging system, which means we need to instrument and provide callbacks for memory accesses. Let's focus on address translation. Doing it in software, translating addresses for memory store to their backing store addresses is way more flexible than traditional page fault handling customization. I'm going to show an example in a few slides, and you'll understand. So if we want to directly access our backing store, we don't really need a paging system and a cache. And we call these type of memory stores direct access memory stores. Let's take a look at the oblivious RAM, or ORAM. ORAM is a well-established security primitive that preserves the input-output behavior of algorithms while obfuscating the distribution of memory accesses such that it hides them from potential adversaries. And it's a well-established security primitive that people have shown that you can use in applications by modifying their memory access to use that. With CoSMIX, it's much easier. You simply need to provide the callbacks for loads and stores, use the ORAM logic inside that, and you'll get obfuscated memory access to whichever backing store you desired. And all without ever changing a single line of code. And this is really flexible. If you don't want to access the storage in every memory access and want to reduce the overhead, we propose adding a paging system, and we call these cached memory stores. So cached memory stores are essentially adding a page table and a page cache, such that we will cache pages inside of a cache and store their translations. And as a use case, we're proposing to use them for in-enclave demand paging. So previous work showed that in-enclave demand paging can maintain the same security guarantees as traditional SGX paging, but removing the cost of enclave exits, therefore boosting the performance. However, this previous work required manual modifications. And with memory stores, it's very easy to do that because we'll only need to focus on the exact semantics of what we need. So the backing store is the untrusted memory, which is software encrypted. The page cache is the enclave hardware protected memory, so it doesn't need to be software encrypted. And the page table maps between them, and we don't only need to focus on what paging actually does, which is decryption and validation of pages. And later on, every accesses to the same memory will be fetched from the cache, so it's much more efficient and doesn't need to be copied, decrypted, and integrity validated on every further access. So memory stores are very easy. They're C and C++ based. It's a small and simple interface, which is function callback, and we provide all the common building blocks. And as an example, it only took us a week, once we had everything sorted out, to implement a memory mapped files memory store. As an end-to-end use case, CoSMIX takes an annotated source code together with memory stores, compile it into binary, and is able to run with different library operating systems inside of enclaves like Scone, Anjuna, and Graphene. As a reminder, we only need to annotate memory allocations, and CoSMIX can automatically infer how to instrument every memory access. So we can mix different memory stores in the same application. In addition, we can also stack memory stores. So we only need to instrument the allocation of a pointer to access it through memory store 1, for example, but memory store 1 also accesses memory, so we can instrument that memory access as well with memory store 2 and stack memory store 1 on top of memory store 2. This is very powerful. So take, for example, ORAM, which performs multiple memory accesses in order to hide the access pattern, which can result in memory trashing, especially when you use it in SGX. To get ORAM, we only need to annotate the pointer's allocation to support accesses through ORAM. But ORAM also accesses memory, so we can annotate that with self-paging, meaning we're going to boost the performance because we're going to reduce the cost of in-enclave paging, but also maintain the ORAM security guarantees, all without ever requiring any code changes being involved. CoSMIX is efficient, and we measured its overhead to be only 20% on the Phoenix suite. And the way it's efficient, it's because it provides selective instrumentation with pointer analysis, reduces accesses to cached memory stores using a software TLB, and also reducing intensive memory accesses, mostly found in loops, by proposing a new transformation that hoists in instrumentation wherever it is able for loop invariant access. And we encourage you to read more about this optimization in the paper. Let's take a look at the evaluation. So we evaluated CoSMIX on different workloads, ranging up to hundreds of thousands of lines of code to show its applicability. We're going to focus specifically on these three next. So memcached we used with about 6 times the available SGX memory, performing random accesses for 1 KB of items, 10% set, and 90% gets. We plotted the throughput latency graph, and running with SGX alone. By instrumenting a single line, annotating a single line of code with in-enclave paging, we're able to boost the performance by more than 2 times. We compared that to a manual modified version of in-enclave paging in previous work, and to our surprise, it was 7% faster than that. We attribute that to the different optimization offered by CoSMIX. We also evaluated on SQLite using an encrypted database file and the KV test shipped with SQLite to perform random accesses. This plot shows the latency to access 4 KB items, where lower is better in this plot. We first configured SQLite to use no page cache and got very poor performance because every access needed to decrypt and validate the database file. Annotating memory mapped files in SQLite, which required only 2 lines of code of annotations, resulted in about 4.5 times faster access because the memory mapped files MStore uses caching and a page cache and caches the contents of the page, eliding the need to decrypt and validate and integrity validate every page. We then configured SQLite with its own page cache, which is manually written, and since it's a production quality application, we believe it was highly optimized. And to our surprise, it was only 27% faster than the memory mapped file offered by CoSMIX, showing that the overheads CoSMIX introduced are not that large. The last example I'm going to talk about is the biometric identity checking server, traditionally used when we travel internationally, for example. The way that works, we have a server that stores a database of images and IDs, and we take a query with an image and an ID and compare the 2 images and output either the image matches the person or not, so true or false. We configured our server with more than 2 times the available enclave memory, so there can be paging activity there. And we annotated the database allocation using ORAM, so we will be able to maintain travelers' privacy. However, ORAM is notoriously inefficient. Our implementation was actually 61 slower than traditional memory accesses. However, with CoSMIX, annotating a single line of code, we were able to reduce that to only 8.6 times slowdown, since we only instrumented database accesses and not every access. So this plot shows the max throughput achieved by the server, so higher is better. However, it's much less than 61 times. But that's not all. by stacking ORAM on top of in-enclave paging, reducing the cost of paging, we were able to further reduce this slowdown up to about 5.8 times slowdown, which might be applicable to some systems. So to conclude, hardware enclaves can improve the security of applications in our public clouds. However, the current hardware support limits the use of trusted page fault handlers, and CoSMIX can provide us the ability to use trusted page fault handlers today, and with efficient instrumentation, we believe this can be a feasible approach. Thank you for your time, and I'll be happy to take your questions.
Marius Koyos, CPFL, thank you very much for the talk. It's not clear to me why do you need to do the instrumentation and which pointers you actually instrument. Do you require some specific domain knowledge in that, and is there risk regarding the actual security of the whole thing?
So I'll recap the question to see that I understood it. You're asking how should I instrument, or which memory should I instrument? So our instrumentation policy is dictated by annotations. We require the developers to annotate their source code, but just the allocation part. So for instance, take mmap or malloc, for example, calls. You need to instrument them. You get back a predefined memory range that you operate on, and CoSMIX can automatically infer how to instrument just that memory region with just that logic, and not other memory region with other logic, using tagged pointer approach.
So it's not all mallocs and mmaps. You need to know which ones you have to annotate.
Exactly. So the semantics is pretty clear in C and C++.
And this affects what goes inside the enclave and whatnot.
Yes, the instrumented application, which compiled to binary, is running inside the enclave.
Okay, thank you.
Sure.
Ed Bignon, EPFL. So again, a great talk.
Thank you.
So your approach to instrumentation is static, if I understand, right? Which means you rely on static instrumentation. You need to do a number of checks, which are necessary. But in the common case, you actually never actually are accessing memory that is subject to paging. So I was wondering whether you've looked at alternative, which is to use a more dynamic approach, where you're optimistic that a memory reference will actually not cause a paging access, and then you rely on some kind of a hardware mechanism to identify the few locations that actually touch memory that is sensitive, and then effectively you trade off the cost of instrumenting memory accesses that actually never become an issue with the one, and by identifying the ones that actually in practice do cause the issue.
So the problem that we saw with the current available SGX is that we can't rely on the available hardware mechanism as it is. Maybe there's some other hardware trick that you could use, but you can't rely on the hardware to invoke your exception handler in the case of paging. Therefore, you cannot rely on the logic being executed there to happen.
Okay. Thank you.
Sure.
Okay, let's thank our speaker again.
Thank you.